Okay, this video I'm going to be looking at my coils as I wind them a little bit different than the bifilar coil. With my coils I put the trigger winding on first, 4 layers of small wire. The wire size doesn't matter, any small gauge wire will do. If the smaller you use, the more you'll get on, the higher voltage but less amps. If you go bigger, you'll get less on, you'll get more amps, less voltage. So the end result current ends up being exactly the same. Now, transistor only needs 0.7 volts to start firing up. So anything between 0.3 and 0.45 gauge will do for your trigger windings. 4 layers on first, nice and even. And then I've got 0.71, 10 layers of that on for the run coil. So to understand what's happening here, you would have to have watched my previous videos on magnet orientation and the results we got from north, north-south and all south out. So we're going to run through the same thing again, only using one of my coils. Record the results. As you can see, this coil is fairly neat. That's the bifilar coil I wound. At the end of this video you'll know why I don't use those. The core is exactly the same material, exactly the same diameter. The number of turns is exactly the same number of turns on that run coil. The only thing that is different, I use a lot less turns on the trigger coil, but I get a lot higher voltage from that trigger coil. So the only thing that's changed since the last test, I've had to add another 100 ohms of resistance in here, otherwise the thing's going to fly to pieces. And this is because, like I said, winding your trigger coil on first will give you a lot higher voltage to the base for less wire than you'll get out of a bifilar coil. So I've got the, like before, make sure that you've wired your coil up so it pushes north pulses out, and as I've done with this one as well, we want to keep it the same. So this test is to see the difference between the way I wind the coils and the bifilar coil. So north magnets out on this rotor, so we'll try that one first, then we'll switch to alternating magnets, and then we'll put the south on, do the same recording and have a look at our results at the end. So I'll just turn the meters on. Like I said, everything's exactly the same as last test, except I've added another 100 ohms in here to bring the voltage back down to around where we had it before. So I've got 760 ohms resistance on the base side at the moment. So we'll give her a spin. As you know, it'll take a little while to pick up and settle. So have a look at my last video and write down the results from that video. What we're actually trying to achieve with the SSG is to get as much out as possible for as little possible input into the system. So we want to be able to charge our battery fairly quick, or as quick as we can, but whilst using as little energy from the run battery as possible. Yeah, another 30 seconds we should be up to speed. Okay, I think we've settled there. So we've got 11.3536 volts. Still going up a little bit. 6, 7. Okay. So our load voltage, we're able to pump this load up to 11.38 volts. As you can see, 106 milliamps. Lighting's not so good in this shed. I'll have to put some more lights up. So there we go. That's 107 milliamps. Okay, that's all. That's our north out rotor. So now we'll try the alternating rotor, as we did in the last test. Our north-south, north-south. Give that a spin up. In a normal situation, as you know, you would have your 100 ohm resistor, 1k pot, and you can fine tune this the same way to get as much out for the least amount in. With this we're set, so the test remains the same over the 3 rotors. So basically, same test as we did before, but I'm just showing you the difference between the way I wind my coils and a bifilar coil, which is wound as per specifications. Another 30 seconds, we should be right. So now it's really starting to wind up, it's just past that point. I probably could have gone down another 100 ohms on the resistance, but hopefully the magnets won't come flying out. The glue doesn't seem to stick to plastic very good, that's why I've got the white tape around them as well. Okay, well I think she's just about happy there. Okay, that'll do us. So we've got 11.3, flicking between 8 and 9, so we'll go 11.38. And our amps, 103 to 104 milliamps. Flicking between the two. It goes to 104, goes to 11.39, and then it drops down to 103, goes to 11.38. So we'll say 104 milliamps for our test on the alternating magnet rotor. So now we'll rip this one off. Here, as you can see, with all our south poles of the magnet out. And we'll run our test again. That bearing sounds a bit healthy now. Now, as in the last video, and you've got your rotor on with all the south out, the rotor will go slower. And the reason of this is because you get one pulse, and one pulse only per magnet. So it's not about rotor speed. What it's about is, like I said before, getting as much out as you can for as little input as you can. So that one's just about up to speed now already. Flicking between 93, 94. Okay, so we got 10.94 volts. And our milliamps are, as you can see, 70. So 70 milliamps, and that was for our south rotor. Now I suppose you want to know, with this setup, this coil, this south out, which is not the norm, not how it's supposed to be done, whether we're getting our high voltage spike back, radiant energy spike, collapsing field spike, whatever you want to call it. So I'll disconnect this charge wire. Most definitely, bright as, definitely there. So that answers that question. It's there with all of the rotors, of course. As you all know, north out will do it with a bifilar coil. But as you can see with this one, very, very strong. Okay, so now what we're going to do, we're going to find out, as we did with the last test, what amperages that it's costing us per volt. So north out was 107 milliamps, so we divide that by our 11.38 volts. So it's a cost 9.4 milliamps per volt under that load. Our next one, alternating magnets, 104 milliamps, divide that by 11.38, 9.13 milliamps per volt under the same load. And then all our south out is 70 milliamps divided by 10.94, and that gives us 6.39 milliamps per volt under load. So that is what's being drawn from our run battery to get each volt into our, what would be our charge battery, in this case our load, which hasn't changed the whole test, both tests. So what you'll need now is the results from the last test we done on our rotors that had the bifilar coil on. So I can give you those right now because I wrote them down. So on our north out rotor with the bifilar coil, it cost us 10.53 volts per, milliamps per volt. Our alternating magnets was at a cost of 8.57. So you will see with the alternating magnets that was a little bit better. Now with our south out, the cost was 8.44 milliamps per volt to the load. So bifilar coil, all north out, was 10.53 milliamps per volt. Combination of my coil with all south out was 6.39 milliamps per volt. So just in doing those two things and a few calculations, in this setup, which hasn't changed, we're now 4.14 millivolts per volt better off. So when we're talking about 12 volts, we times that by 12. Under the same conditions, we would be using 49.68 milliamps less with this combination than with the standard Bedini SSG setup. So that to me is a pretty big saving. Well worth the experimentation that I've been doing. Definitely the setup I'd use. A primary winding, secondary winding coil with all south out, as you've seen, is much better than your bifilar coil, which is pretty neat, pretty tidy, wound to specifications. So a lot better than your bifilar coil with all north out. Plus the other problem, as some of you will be finding out, your cores are becoming magnetised this way they never will, because it pulses north the same amount of times as the south passes, so it remains neutral. Alright, next I'll show you on my next video how to wind the coils the way I do them for the best efficiency. Till then, bye for now.